Hi, I'm Analytical, and welcome to Beyond Binary, Class 2, Ode te airway, unage, eBay, okingte, about yay, ekrits say, and yay, odes k. Today we're going to be talking about secrets and codes. This is the third episode in my series Beyond Binary, so be sure to check out the first two videos before watching this one. A link will be in the description below, and while you're down there, be sure to give the video a like, subscribe, and ring the bell. Today, we're going to be talking about secrets. One of the original uses for computer science was to send secret messages to other people. A very common use for this was in war. Ugh, gross. Back then, people were typically sending texts as secrets, but we could also send pictures as secrets too. And one of the extremely prominent computer scientists, Alan Turing, was a major player in this field. And like us, or at least like me, he was a homosexual. And he helped crack the codes that the Nazis were using and helped us win World War II. And thank God he did, because as a queer Jew, I am not interested in letting anybody take that away from me. No thank you. So today, we're going to be looking at the computer science of storing secrets and decoding them. And the name for this in computer science is encryption. And if we want to decode a message, we would call that decryption. In class 0, we saw that we could represent text and images with binary numbers. If we want to encrypt either text or an image, we're going to need to revert those text and images all the way back to binary, or maybe just into numbers, and change those numbers around and then reconvert them back to a text or an image. So to do this, we're going to need to know a little bit more about how binary works. It is time for you to learn how to read binary, because reading binary is what? Just ones and zeros, actually. The way computers represent text is each letter will be represented by a number. Then those numbers will be represented by binary numbers, and those binary numbers are just going to be represented by our favorite skinny legends, transistors. Every computer has a limited number of transistors. Your computer, your phone, when you get those running out of storage error messages, it's because all the transistors are currently being used. In this day and age, your phone and your computer have gigabytes and gigabytes and maybe even a terabyte of memory. But back in the day, each computer had a very limited number of transistors, so computer scientists had to be very careful with how many they were using. A group of computer scientists got together and decided we're going to represent text with 7 bits or 7 transistors. With 7 bits, there are 128 unique combinations we could do, so we can store 128 different letters or symbols. My hair may be extra huge today, but I'm not storing extra brain power up there. The number 128, I'm not just pulling out of thin air. Let's dive in to figure out how we got that number. And math warning, math warning, math warning. Math warning. I know I told you, there's not going to be a lot of math in computer science, or not even any required to do computer science. Well, to get through this next section, we're going to need to use a little bit of elementary school level addition and multiplication. We're going to get through it together. I'm going to hold your hand. If you are really math-averse, skip to the following time and I will let you walk away unscathed. But maybe once you've watched through this episode, come revisit it and give the math a second chance. All right, now let's dive in a little bit more to binary numbers. In class 0, we looked at having 2 bits to represent your sexuality, 1 bit for into men, 1 bit for into women. And we could have each of these be up or down. So we'd have 4 combinations here: down, 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 up, down, up. And I said we could represent down with 0 and up with 1. So we'd have 0, 0, 0, 1, 1, 0, and 1, 1. These represent numbers 0 through 3 in binary. 0 through 3, you might be thinking, but I like to start counting at 1. What's the deal? Because we decided that transistors are all going to start at 0 and computer scientists wanted to be as efficient at storing the data as possible, they decided to include 0 as the first number. And that is why computer scientists start counting at 0. Even in this class, Beyond Binary, we started at class 0, not at class 1. So now that you are a computer scientist too, it is time for you to start counting at 0. And you better get into it. In order to read these numbers, we actually go all the way back to elementary school when you were learning to read numbers. Let's say we've got the number 169. In elementary school, you might think about it like 9 in the ones place, a 6 in the tens place, and a 1 in the hundreds place. We could also express this number as 1 times 100 plus 6 times 10 plus 9 times 1. 169. Each place is increasing by a power of 10. We have the ones place, the tens place, or 10 to the first place, then a hundreds place, which is 10 squareds place. Then we'd have the thousandth place, which is 10 to the third or 10 cubed, and so on. And binary, instead of having tens as our bases or as our places, we're just going to have twos. So we'll have ones place, twos place, fours place, eighths place, 16s place, 32's place, and so on. If we have the number 1, 1, we can break it down the same way. That's 2 plus 1 equals 3. Or a bigger number, 1, 0, 1, 0, 1, is 16 plus 0 plus 4 plus 0 plus 1. And that's 21. Blackjack! Honestly, though, you are very rarely going to be asked to interpret a binary number or to figure out what the actual value of it or decimal number is from a binary number. And no one's going to hand you an 11 and be like, oh, that's not 11, that's actually a 3. Because if they are, they're just being annoying. If it's a binary number, there will typically be some indication that it's a binary number and that you should interpret it as such. So if we have 7 bits or 7 places, that means we'll have 2 to the 7th amount of values. And 2 to the 7th is 128. To think about it a little more intuitively, when we have one transistor, we have 2 values. Then when we add another transistor, we still have those 2 values, but now we have this other transistor. So now we can have those 2 values while our new transistor is up, and we can have those 2 values while our new transistor is down. So therefore, we've doubled the amount of value. And if we add another transistor to that, we have 4 existing values and a new transistor. And we can have those 4 existing values while that transistor is off, and those 4 existing values while that transistor is on. So when we keep adding transistors or we keep adding bits, we're just multiplying the amount of possible values by 2. Math, 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 math. And that is why we have 128 unique values we can store in 7 bits. And welcome back to our non-math friends. Hi! There was a tragedy when these computer scientists decided which 128 characters or unique letters or symbols they were going to include, and emojis weren't one of them. There were no emojis. All they gave us were numbers, letters, and a bunch of symbols. In class 0, when I said let's assign numbers to letters, I said let's make 65 the letter A. And I was not just feeling très random that day. The computer scientists that decided this created a table, and it is called the ASCII table. And this is a guide of all of the numbers to their symbols. Well, one moment I have a bad joke that I want to read. I'm just trying to share the key to my heart with men, but all they want is my ass key. Ugh, disgusting. I'm just gonna delete. Oh my god, I'm a mess. If we look at the ASCII table, we can see the digits, letters, and symbols, and everything else that's not shown are just hidden characters that make your computer run, like an end-of-file character or a start-of-file character for that instance. Okay, we are 10 minutes in, and how does any of this help us write secrets, share secret messages, crack codes, send codes? How do we do it? Well, if we have the numbers, what we can do is change them in interesting ways. Let's say we have a lowercase letter. If we want to turn it into an uppercase letter as maybe our code, all we have to do is convert that lowercase letter into a number, subtract 32 from that number, and then convert that number back to a letter. Then we've got its uppercase one. So our code is converting lowercase to uppercase. So secret. And obviously that is the worst code or worst way to share a secret ever. Just converting it into uppercase letters, like, what? That is not a code. Your encryption is terrible. 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 Your encryption is terrible. 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 A more secret code we could do is take each letter, convert it to a number, add 5 to that number, and then convert it back to a letter. A would be F, B would be G, C would be H, and then at the end we might have to wrap it around. So W would be A, X would be B, and so on. This encryption method is called a Caesar cipher. Caesar cipher? Now I ordered a Caesar salad. Let's go check some of this out in JavaScript. We're going back to Codepen using the template from last class, and we're just going to print out a string. We'll just print out my name for now. Strings in JavaScript have a bunch of functions built into them. Here's a page that lists them all, and I can link this below if you want to look into it more on your own, but I'll bring to attention the ones we're going to use. One that we have available is .length, and this will get the length of the string. So this is a 12-character string. Another thing we can do on this is access individual characters within this string. So if we use the square brackets, and then we type a number between 0 and 12, not including 12, we'll get the character at that location. So if we do 0, we'll get capital A. If we do 1, lowercase n, 5, capital L, and so on. Let's copy this down a few times. The function we are really after is car code at. Here they have an example of how to use it, but you can also just watch me use it right now, right here. So to use it after a string or even after a string variable, we would type .car code at, and I have a bit of auto completion turned on. If we don't pass it anything, it will get the character code for the first element. So that's capital A, which we said was 65. Let me use the boring print for this so it's a little clearer to see. If we want to get the character code for capital L, we would put 5 in there, 76. And if we want to turn any number back from its character code, we would use the function capital string dot from car code. So we could put in 65, and then we'd want to just print that out. And we get our capital A. Or if we want to put 76 in, which would be capital L, we'll see that we'll get that capital L. And if we want to play with a code similar to what I was talking about before, we could convert this capital L into a lowercase l by adding 32, which is the distance from the lowercase letters to the capital letters in our ASCII table. To make it a little more clear, let's create a variable to store this distance so we aren't hard coding it. Let lowercase distance equal a.carCodeAt minus lowercase a carCodeAt. So let's also spell that correctly, and then we can add that to 76, and we'll actually have to subtract it from 76, and then we'll get our lowercase l. And if we wanted to go the other way using the lowercase l, we would just add that difference. With this, we could create a new function that would convert all strings into uppercase strings. We can also practice writing functions again. To create a new function, we type function, then the name, so toUppercase, parentheses, curly braces, and we probably want to take in some sort of message as the parameter to this function. Let's comment some of these lines so we have a bit more room, and there's a shortcut command / and that will comment them, and if you do it again, it will actually uncomment them to make it super easy. We're going to need to use everything we just learned about strings to get this done. We know that we want to make a change for every single letter in our message. So we want to use a for loop for this. We'll do for let I equal 0, semicolon, while I is less than the message length, I++. To get the individual letters in the message, we'll use our square brackets and we'll access it at I. So we'll get the 0th element, the first element, the second element, all the way up to the message's length -1. So we're going to hit every single letter. For now, why don't we just print each letter, and let's use the glitter print for this. And we're not going to print them on separate lines because we want it to come out all at once. So we type message, and then to get each piece of the message, we use I. We're going to use the square brackets on the message. And we cannot forget to call toUppercase on this. So for now, we can just throw in analytical in there. So the first thing we need to do is take this letter and convert it to the character code. Let's create a new variable for this so it's a little more clear. Let carCode equal message I.carCodeAt. Now we have the car code. We can do character code plus equals this lowercase distance, and then we'll do print glitter using our new character code. Well, we certainly got close, I guess. I don't know who Lytical is. All the lowercase letters worked fine, but the uppercase letters and the spaces got converted, and we didn't really want that. So let's add an if statement in here to only apply this transformation if it is a lowercase letter. We know it's a lowercase letter if its character code is between the codes for lowercase a and lowercase z. And if we wanted to, we could prompt some queen for whatever message they wanted to have uppercased, like so. And then we pass the prompted result just into our toUppercase function. Run this script. It me, Anna. Too many A's. That's what I get for not looking at my keyboard. Whatever. That is all the stuff we're going to be doing with text in this episode, but at home, I want you to make your own Caesar cipher. You or your friend are going to type in a message, and then that message will get encrypted. And you can choose whatever offset number you want to use. And then I want you to create a decrypter. You'll be able to take some kind of message that's been created with a Caesar cipher and convert it back to the original message. You might need to use a little bit of math here, especially when you're wrapping from the end of the alphabet all the way back to the start of the alphabet. One math operator in computer science that I didn't show you last class is the percent operator or the mod operator. This will give you the remainder when you divide one number by another. So 5 mod 26 will be 5, 6 mod 26 will be 6, 7 will be 7, but when we do 31 mod 26, we'll get 5, 32 mod 26 will get 6, and so on. So you could use that to help wrap around all your numbers. On this channel, we love sharing images, so why shouldn't we share secrets that are images too? I've got a few secret images on the screen, and it is going to be your at-home assignment to decrypt these images. Last class we saw that an image was a collection of pixels, and pixels were just a group of numbers. In JavaScript, pixels are 4 values. There is red, green, blue, and a transparency value. And each of these values are 8 bits, so 2 to the 8 is 255. So we can have values from 0 to 255 in here. So in JavaScript, an image is just a list of pixels, and a pixel is just a list of 4 values. And if we think about it, a string is really just a list of characters. But if we want to represent this list of numbers, how would we do that so that we could take these numbers, change them around, and encrypt them for our secret images? Let's go back to Codepen. Let's open up a new pen, and we'll create one from this template. The way to store a list of data in JavaScript is called an array. So we can create a new variable, and we can just call this array so it's a little clearer. And to define an array, we'll use square brackets. So we'll have an opening square bracket and a closing square bracket. Any data or variables we put in here will just separate with a comma. We could have an array of strings, we could have an array of numbers, we could even have an array of both. But it's typically best to only have one kind of data in your array. We can print out our array. And like with strings, we can also get the length and access individual elements within this array. We'll use getPixelArray, and this will give us an array for an image of a width and height that we specify. This will give us a list that has 100 by 100 sets of 4. Every 4 will have red, green, blue, and transparency. And then we'll have those repeated over and over again 100 by 100 times. Then we'll use the draw function, passing in that same width and height and the array of image data that we're going to modify. If we want to make the first pixel red, we would set the 0th element in this array to be 255 and the 4th element, or index 3, to be 255 to turn the transparency all the way up. It is definitely a little confusing. That is the 4th element, but we call it the 3rd. I totally feel your pain. Now we run this, and if we zoom in all the way, we can see that there is 1 red pixel. It's probably going to be best if we use a for loop for this. So let I equal 0, I is less than image.length, I plus plus. And actually let's do I plus equals 4. That way we're looking at 1 pixel every time the loop goes. We can move those in here. And now we set I equal to 255 and I plus 3 to 255. And now the whole block is going to be red. If we wanted it to be green, we could do I plus 1 equals 255. Or blue, we could do I plus 2 equals 255. Even if we aren't changing each of the colors, it's probably best if we list them all out anyway. And we could even add a comment to make it a little more clear what we are looking at. I plus 1 is green, I plus 2 is blue, and I plus 3 is transparency. And the color combinations here are going to work a little different than you're used to. Feel free to play around with it and see what you get. If you'd like me to make a separate video with how colors work in JavaScript or on the web, let me know and I'd be happy to share my knowledge on all of that. If we want to play around with this a little more to try to make some kind of photo or picture, we could play around with some of these numbers. We could copy our entire loop down. Instead of going all the way to the length, we can go maybe to the length divided by 2 or something. And maybe we change red to be 255, green to be 0, blue to be 0, and transparency to be maybe 128. We can run this and see what we get. And now we get a half red on there. One thing we could do is use the existing values and transform those in a certain way. We could take the green value for this image and maybe use it only at 10% for the red value. We can run it again and see what we get. And now we kind of get a gray. There are so many different combinations of what you can do with this. And now we can bring it all the way back to how we would decrypt one of these images that I've got here. At home, I've got helper functions that will load in all of these images as their pixel arrays. Then I'm going to need you to modify some of their red, green, and blue values so you can figure out what the hidden images are. I've scrambled the blue and the green values, so the true image is only in the red pixels. So what you're going to need to do at home is remove the blue parts of the image, the green parts of the image, and scale up the red part of the image so that you can see the hidden images. That is all I have today for you about encryption, codes, a little bit more about binary, a little bit more about strings, learning arrays. We've covered so much in this lesson, and at home I am so excited for you to have the opportunity to try being a code cracker. All of the links and more information for the at-home work will be in the description below. But just to review what you're going to do, you're going to create a Caesar cipher, and then you will create a tool that will help decrypt a Caesar cipher. And then you're going to take a look at these secret images that I've got for you, and you will crack those codes. If you loved this video, leave a like on the video, subscribe, and ring the bell. If you have any questions, leave them in the comments below or send me a tweet at @theanalytical. Thank you so much for watching, and you better crack those codes. Bye, everybody.